Hello, everyone. Welcome to our final MOCS presentation. Our model is entitled The Impact of Common Mycorrhizal Networks and Differing Reproductive Strategies on Successional Forest Composition. A little bit of background. We used red maple and white pine as our model taxon, and we simulated early successional northeastern forest, which means right after a disturbance that removes all of the present species. We also included some different reproductive strategies, including investing in oneself or investing in one's offspring. And finally, we included the use of common mycorrhizal networks, or the fungus that grows on tree roots and helps trees share nutrients. Our research questions were, how does the presence or absence of common mycorrhizal networks impact the growth of an early successional forest plot? And also, how does use of common mycorrhizal networks and our reproductive strategies change forest composition? Our research objective was to create a biologically relevant two-species forest successional model for an early successional Vermont forest.
For the model itself, we created a spatially explicit network model placed on a grid where each node represented a different tree, either a maple tree or a pine tree, and they were connected by mycorrhizae through the edges. And they also had a currency system for their nutrients, where each tree was allotted a certain nutrient budget for each iteration of the model. And using this budget, trees were either able to grow itself, reproduce and create a new node, or share its nutrients through its neighbors connected through the mycorrhizal fungi. And throughout this model, for each iteration over time, we tracked the node attributes of species, position on the grid or in the forest, the amount of nutrients that each node has, and also the root radius of each node, which was a proxy for how long the mycorrhizal connection was. Some key parameters that we tried to keep them biologically relevant. So for example, maple trees prioritize growing its own root radius, whereas pine trees more often send nutrients to its neighbors. So pines were more likely to create the edges, whereas maples were more likely to grow its own root radius. We also had some key assumptions that were not as biologically sound. For example, there was no competition between the tree species, and there was also no carrying capacity, such as there were limitless nutrients. And this was less biologically relevant, but made the visualization a little easier. There was also no tree deaths, or visualization kept growing, and there were also no climatic or seasonal patterns. And we also generalized nutrients, whereas in reality, these different nutrients might cycle through the forest differently. And there are ways that we could add those parameters in later, but those are assumptions that we had for now.
The initial conditions of this model were designed to simulate early successional forest system after recent disturbance. The plot started off empty, and we began by seeding it with one maple tree and one pine tree to act as seed species for the rest of the forest. Each of these nodes started with 50 nutrients, a root radius of 10, and an initial position that we gave it on the grid somewhere around the center of the plot. Through each iteration of the model, we ran this update function, and at the beginning of it, each node would gain nutrients proportional to its root radius, 2 times its root radius. And then with the available nutrients that it had, the tree would then, through different probabilities, do one of 3 things: grow itself, reproduce by creating a new node, which is assigned to a random position on the grid, and given some initial nutrients, as well as the species attributes as designed by its parent. Or it could, through any edges that are currently existing, share nutrients with its neighbors that may need it. And then at the end of that step, the tree then also has an option to create edges with nodes that are within range of its root radius and are more likely to create edges with its own species than other species. Here we have our first representation of the model without a mycorrhizal network. In pink, you can see the pine trees. In purple are the maple trees. This is a 5 by 500 grid showing 17 time steps. And the sizes that you see here are directly proportional to the root radius. In this visualization, we have the network running with mycorrhizae available, as you can see, with the edges starting to form between the different nodes, more preferentially toward the pine trees as well, as they make mycorrhizal networks much more than maple trees.
All right, so the next few slides are going to be presenting some other results of our model runs. This slide here is showing the total number of trees with pine trees in green and maple trees in yellow over the 17 time steps that we looked at. And we ran each one 10 iterations. So that's what all the different lines represent, and ran it with mycorrhizae on the bottom and without mycorrhizae on the top, the two networks that we showed in the previous slides. We did this type of visualization to kind of see the variation between runs, since our model did have a stochastic component with some random number die rolls happening to decide some of the probabilities for the different strategies. Overall, the runs showed similar trends. In all cases, pine trees tended to have, there tend to be more pine trees growing over time than maple trees, as you can see with the differences between the colors. This slide is a similar type of plot, but instead on the y-axis, we're plotting the average root radius of each type of tree across the model runs and across time. As we can see, the average root radius is higher for maple trees than it is for pine trees. And there is a little bit more variation in this parameter between the 10 model runs, which we thought was interesting. So next we kind of looked at some of the results at the end of the 17 time steps. So these plots are showing the average root radius at the end of our model run for both maple on the left and pine on the right. And then within each graph, the bar on the left is the network without mycorrhizae, and the bar on the right is the network with mycorrhizae. And we were a little bit surprised by this. So we found that the presence or absence of mycorrhizae didn't impact the average root radius, which we thought it potentially would. But you can see these error bars are really overlapping. And so we didn't find a significant difference with or without mycorrhizae. However, we did see one impact of the mycorrhizae on our network. So we found that it impacted the distribution of the final sizes of pines. So this figure shows root radius frequency distribution for just the pine trees, both with and without mycorrhizae. And as you can see on the top, we have a couple trees that grew really large without mycorrhizae. And they were able to grow that large because they weren't sharing any nutrients, since they weren't connected with anybody else through mycorrhizae. And finally, we ran some network analysis on our mycorrhizal network model. This slide shows some of those metrics averaged over 10 runs. Again, we had an average degree of all of the nodes of 3.65. So on average, they had 3.65 neighbors. But this value was really different between maples and pines because of their differences in creating edges through mycorrhizal connections. So this graph on the right just shows the average degree of maples on the left and pines on the right. You can see they had vastly different numbers of neighbors, which we kind of saw in the visualizations before, where the pine trees were much more connected than the maple trees. And this network had a density of 0.00564. So it wasn't super dense, but that's kind of an average density value over 10 runs.
So overall, we found that we did successfully generate a model that can demonstrate the effect of different growing and reproductive strategies in an early successional plot. The tree species that prioritize sharing nutrients, or pine, saw more offspring than those who prioritize growth, whereas those who prioritize growth tended to see a larger average root radius with a comparison to the other. Pine trees were more abundant but smaller than maples, and we did not find a difference, a statistically significant difference in growth or reproduction when common mycorrhizal networks were removed. We definitely recognize that there were a lot of variables here. And so in the future, we might like to normalize across one variable to look at the other, like giving both trees the same reproductive strategy to isolate the impact of mycorrhizae, or incorporate some more biologically relevant parameters like tree age, tree death, forest carrying capacity, or the patterns of seasonality. Here are our references, and that's all we have. Thanks so much.